So today I'm going to record for lecture 4, which we're going to cover the R-mean, N-mean and special cases. Okay, so at the end of this class, you should be able to identify the limiting cases in operating the distillation column in terms of reflux ratio, specification, and number of plates determination. Number 2, able to determine the minimum reflux ratio for a given specification of a distillation process. Number 3, to determine the minimum number of plates at total reflux, both by graphical and analytical method, i.e. using the Fenske equation for the analytical method. Number 4, to derive the operating line equations at various special cases by rewriting the material balance equations in the column. And finally, able to apply the McCabe-Taylor method for special cases of distillation processes, including the stripping only column, rectifying only column, direct steam injection, and rectification tower with side stream. Okay, so let's have a look at the first limiting case, which is the total reflux. Okay, so what is total reflux? Okay, let's say you have a distillation column for a binary mixture, A and B. So let's say you have the feed conditions specified, the distillate composition and bottom compositions are also specified. And then here the number of theoretical plates, and if you want to calculate, must be based on the specifications like what we did before in lecture 3, right? So you know the feed condition, the XD distillate composition, and the XB bottoms composition. So this number of plates N depends on the operating lines, and the operating line depends on the reflux ratio R, because if you recall, the operating line equation is yn plus 1. Okay, yn plus 1 equals to R over R plus 1 xn plus xd over R plus 1. So since n depends on the operating lines and operating line depends on the reflux ratio, so reflux ratio actually has a lot of influence, or it's a determining factor towards the number of plates. So we need to know what are the limiting values of the reflux ratio that we can operate with. So one of the limiting values of reflux ratio is the total reflux, i.e. when R equals to infinity. So you know R is ln over d. Okay, the ratio of liquid returned back to the column divided by the d, the liquid withdrawn as the distillate product. So when R equals to 0, meaning the d here is, when R equals to infinity, meaning the denominator here, the d equals to 0. Okay, so what happened when d equals to 0? So at the total reflux, okay? So at total reflux, meaning everything, all the vapor that we have produced, we have condensed into liquid, everything is being returned back to the column. So all condensed vapor is returned back to the column, hence there is no product, therefore the d equals to 0. And then all the bottoms liquids is reboiled and vaporized and returned back to the column as well. Hence, there is no bottoms product, thus B is also equals to 0. So, when D equals to 0 and B equals to 0, this can only mean that F must be also equal to 0. So, this is consistent with the lack of influence in the feed condition. You know, this is assuming after a steady state has reached, then we stop feeding the distillation column with F. So then we stop withdrawing the distillate liquid and the bottoms liquid, and instead we return back everything into the column. Okay, so what happens when we do that? Okay, so let's recall from the derivation of the ROL from the material balance equation. So what happens at the top of the column is, okay, when you have the top here is Vn plus 1, and then this is Ln, and then this is D. So from material balance, Vn plus 1 equals to Ln plus D, and that from the ROL, you have this equation. Okay, this is just from the component material balance from the overall material balance. So what happens at total reflux? So when total reflux D equals to 0, and then Vn plus 1 must be equal to N, because now we don't have the D here. So Vn plus 1 equals to Ln. Thus, this ROL becomes just Yn plus 1 equals to Xn, because this one is 0. And then ln and vn are the same, so this one is just equal to 1. So you get yn plus 1 equal to xn, or simply just y equals to x equation. So you know what is y equals to x equation? Is the 45-degree line across the y and x axis on the graph paper. So similarly, we can do the same for the SOL. So what happens at the bottom of the column is that, so this is your reboiler, so this is your B, and this is the Vm plus 1, and this is your Lm. So from here, you know that Lm equals to Vm plus 1 plus B, and thus rearranging, you get this Vm plus 1 equals to Lm minus B. And when you rearrange, you do component material balance and you rearrange to put Ym plus 1 as the subject, you have this SOL here. So at total reflux, B is also equal to 0. And then, because here we don't have B withdrawn, so thus Vm plus 1 will be equal to Lm. Thus, this SOL will become, so since this is already 0, okay, and this is just equal to 1, so you have Ym plus 1 equals to xm, or simply just again the y equals to x equation. So from here at total reflux, both operating lines becomes y equals to x equation, y equals to x line, and this will give you the minimum number of stages and min when we have the total reflux ratio, I mean when R equals to infinity. Okay, so we can have a look at the graphical representation of what happens to the ROL and SOL. So let's say the curve here is your VLE. Okay, so the x-axis here and y-axis here for your more volatile component. So let's say this is your XD and this is your XB here. Okay, so at total reflux, the operating line becomes y equals to x. So typically when you want to plot your operating line, you have the ROL, at least the point is XD, and the SOL, you have the one point is XB, right? But now, since the both ROL and XOL becomes y equal to x, then it overlaps each other, and thus the whole y equals to x line are both representing the ROL and SOL. Okay, so from here you can calculate the number of stages, and if you calculate the number, if you step off the stages starting from XD, okay, and then you stop when you reach XB, this will give you the minimum number of stages happening when R equals to infinity, at infinite reflux ratio. Okay, so when actually the distillation column operated at total reflux, so actually in real industrial practice, of course, we will not operate it at total reflux because we would want to withdraw the liquid product. But this one is operated at total reflux in the case where we need to facilitate experimental measurement to calculate the tray efficiency, because at this stage, a steady state operating condition can be readily achieved. And distillation column operating at total reflux and minimum number of stages will thus require infinite size of condenser, reboiler, and distillation tower diameter for a given feed rate. So we will have a look at this in the later weeks of the course during the design of the distillation column on how the total the reflux ratio affects the area and the size of condenser and reboiler requirement also. Okay, but here the point is, if you want to calculate the total reflux, what you can do is using graphical method is to plot the y equals to x line combined with the VLE line, and then from here you specify the XD and XB, and then you can simply step off the stages from XD to XB to determine the minimum number of stages. And another method to calculate the total reflux is the analytical equation. analytical method using Fenske equation. In this case, you don't have to use graphical method. Okay, so let's do a derivation of Fenske equation. Okay, in this case, for a special case of ideal mixture, a simple method, i.e. when we say simple method, we don't have to use any graph to calculate the N mean given the specification of XD and XB. So this is based on the relative volatility of the two components, alpha AB. Okay, so we start with the definition of the relative volatility alpha AB. So alpha AB, as you know, alpha AB equals to Ka over Kb, and Ka is Ya over Xa and Kb is Yb over Xb. So if the mixture follows Raoult's law, and thus we can use this Raoult's law general term here to rearrange. So from here you can get Yi over Xi equals to Pi set over P. So from here you can rewrite the alpha AB to be equal to this term here, okay? So PA set over total pressure P divided by PB set over total pressure P, and you can eliminate this P. So alpha AB equals to PA set over PB set. And the ratio of a vapor pressure of A and B does not change much over the range of temperatures in a typical column. Because you know vapor pressure is dependent on the temperature, and throughout the column the temperature is not constant from the bottom to the top of the column. The bottom is the higher temperature and the top has a lower temperature. So there's a temperature profile throughout the column. Thus, because saturated vapor pressure depends on temperature, you will have different PA set and PB set at different trays throughout the column. However, we assume that if for special cases of ideal mixture where we can assume the constant alpha AB is not because the vapor pressure is constant throughout the column, but rather the ratio of the vapor pressure of alpha A and B is the one that is constant, not the PA set or PB set, okay? So we assume this, that the ratio of the vapor pressure of A and B does not change much over time. Thus, we can take alpha AB as a constant to derive the Fenske equation in the next step. Okay, so for a binary system, XB equals to 1 minus XA and YB equals to 1 minus XA. And just now, alpha AB is equal to YA over XA divided by YB over XB. And this one you can rearrange into YA over YB equals to alpha AB XA over XB. So from here, you can write the relationship as this equation here. And for plate n plus 1, you can say that yn plus 1 equals to 1n plus 1 divided by 1 minus yn plus 1 equals to alpha AB times xn plus 1 divided by 1 minus xn plus 1. Okay, because XA and YA, just a relationship for the more volatile component A here. Okay, so at total reflux, Yn plus 1 equals to Xn. We have established how we got to this point just now, assuming D equals to 0, not assuming at total reflux really D is equals to 0. Thus, Yn plus 1 equals to Xn. So you can replace this Yn plus 1 equals to Xn inside this expression and you get to this equation. Thus, you get Xn over Y minus Xn equals to alpha AB times xn minus xn plus 1 over 1 minus xn plus 1. Okay, hope you're following until here. And then we have a look at what happens at the top of the column when total condenser is used. So total condenser is the one that converts everything, all the vapor phase into liquid phase. Thus, in a total condenser, the composition does not change. Okay, so just re-illustrate it again. So this is your condenser. Okay, this is your column. So here you have V and Y1. Here is XD. Okay, because this is your plate number 1 at the top of the column here. So this is the vapor leaving the plate number 1 is Y1. And the liquid leaving plate number 1 is X1, the composition X1. Okay, so here at the top of the column, if a total condenser is used, thus Y1 will be equal to XD because there is no change in the composition. So you can replace this equation here. Okay, we follow through. This will become XD equals to XD over Y minus XD equals to alpha AB times X1 over Y minus X1. Okay, and then subsequently, for a succession of n number of plates, so you can just, this is for plate number 1 here. So what happens at plate number 2? Plate number 2, we follow this relationship. Okay, so at plate number 2, yeah, you just replace this n with 1, and thus n plus 1 becomes 2. Okay, and then you repeat the same thing. Okay, let's just to help you illustrate things better. X2 over 1 over x minus 1 minus x2 equals to alpha AB, x3 over y minus x3, and subsequently x2 over y minus x2 equals to alpha AB, sorry, what am I doing? No, this is x2, this is x3, okay? So this is x4. And so on until you reach n here at the end of the column. Okay, so next, what happens? So let's say if all the sets of equations from each stage, starting from the top plate, are multiplied together and the intermediate terms are cancelled. Okay, let's just have a quick look on that, how it happens there. Okay, so we started with just now xd, y minus xd equals to alpha AB x1 over y minus x1. So this is your equation 1. And then x1, y minus x1 equals to alpha AB x2, 1 minus x2. So this is your equation 2. x2 over y minus x2 equals to alpha AB x3, y minus x3, so this is equation 3, and so on until you reach xn minus 1 over y minus xn minus 1 equals to alpha AB xn over y minus xn. So this is your equation n. So what happens when you multiply 1, multiply 2, multiply 3? Okay, so what you'll have is xd over y minus xd multiply with x1 over y minus x1, multiply with x, I continue down here, okay? And will be this, finally, xn minus 1 over y minus xn minus 1 here will be equal to alpha AB times alpha AB times alpha AB times alpha AB until n times, n number of times, and then you have x1 times the x2 times the x3, and finally you stop at xn, y minus xn, right? So the terms here you can eliminate, the middle terms, all this you can eliminate, and finally you will end up with xd over y minus xd, yeah, equals to alpha AB to the power of n times xn over y minus xn. Okay, so this, our job's not finished yet. We're just going to show you how the derivation of the Fenske equation. Okay, sorry, I take time to erase this writing. Just pretend like I'm keeping the annotation because I still want to keep the ones that yeah, okay. Let's have a look again at this slide. So you know that, okay, I've shown you what happens when the equation from each stage are multiplied together. So you will end up with xd over 1 minus xd equal to alpha AB to the power of n times xn over 1 minus xn. So to reach the bottom discharge of the column, then this n here, we put it as n minimum plus reboiler, okay? Because we always want to indicate whether or not our calculation includes a reboiler or not, Okay, so we put it as this reboiler is just one extra stage. So there's n equals to n min plus 1. And at the bottom of the column, xn will be actually equal to xb. So we can further simplify this equation to give something that gives meaning to us instead of n. So we have alpha AB, and the n here is to the power of n min plus 1, referring to the minimum number of stage plus 1 reboiler stage. And instead of xn, we have the xb, indicating the composition of the more volatile component in the bottom liquid product. So for this, we want to find, the goal is to find n min. So solving for n min by logarithm gives this equation here. Okay, you can try to rearrange, make yourself satisfied. So you have this equation. So notice this minus 1 here. So this is minus 1 reboiler. You may find various versions of Fenske equation. Sometimes you don't see the n min plus 1, it's just n min. So when there is no indication of the plus 1, we have to assume that it includes the reboiler stage. Meaning, if for this equation here, if you don't have this minus 1, meaning whatever is on the right hand side here includes a reboiler. But to indicate that we exclude the reboiler, that's why some equation minus 1 in advance before we have to think whether or not it includes the reboiler, because from the derivation here the plus 1 refers to the extra reboiler stage. Okay, so this is the guy Merrill R. Fenske, who derived the Fenske equation to help us to find the minimum number of stage using analytical method. Okay, so this Fenske equation applies when alpha AB is a constant. If there is a change in the value of alpha AB from the bottom to the top of the column, if the change is moderate, we can use a geometric mean of the alpha AB. So how do we get the geometric mean of the alpha AB? Is this part, okay? Here, alpha AB geometric mean is alpha 1 times alpha B. Okay, so this alpha 1 is the alpha at the top of the column. Okay, so you have to always visualize what happens inside your column. Okay, so this is your XD, so this is your Y1, so this is your plate number 1. So Y1 would be equilibrium to X1, i.e. the liquid leaving the plate number 1. Okay, Y1 is not in equilibrium with XD because Y1 is actually equal to XD. So how do you get alpha 1? Alpha 1 is the alpha at the top of the column. Okay, so alpha 1 equals to alpha AB at top of the column. So from here, you need to be able to read the VLE equation, not equation, the graph. So this is your Y, this is your X. So let's say Y1 equal to XD, right? So you just take this to be, this one is XD and then XD. So XD is actually equal to Y1. So what is X in equilibrium to Y1? This is X1. So this is your Y1 equals to what? YA at plate 1 over XA at plate 1. So if you got YA and XA, then you get the YB at plate 1 and XB at plate 1. Similarly, for the bottom of the column, if you want to find out what is the alpha at the bottom of the column, you also have to visualize what happens at the bottom of the column. Okay, so you visualize because it is actually an equilibrium stage at the bottom of the column, right? So this is your bottom of the column. So this is your reboiler. So here is your V and XB, and then here is your VM and YM plus 1. Here is your LM and XM. So here YM plus 1 is the composition of the vapor that is in equilibrium with XB. So when you want to read from the VLE curve, so let's say this is your XB, so you just simply go to the VLE curve to get what is YM plus 1. Okay, so then you can calculate the alpha B. Alpha at the bottom of the column is y of A at the bottom divided by x of A at the bottom divided by y of B at the bottom divided by x of B at the bottom. So, just be careful. So this value here refers to the composition of A at the bottom, and this ym plus 1 value here refers to the composition of A at the bottom, and then you get the composition of B at the bottom by just 1 minus the composition of A, both in the vapor and in the liquid phase. So that's how you get alpha B, and that's how you get alpha A. Then only you calculate the geometric mean of alpha AB by just substituting the numbers inside here and getting the square root. Okay? All right. So yeah, this is the definition of the terms alpha 1 and alpha B. Okay? So that is about the minimum number of stage. Next is we want to look at the next limiting case, i.e. the minimum reflux ratio. So previously in lecture 3, when you are asked to use McCabe-Taylor method to calculate the number of stages, you are given the value of R, the operational R. Okay, you're given R, then you can calculate, you can get the ROL, because then you can just get the Y equals to mx plus C once you get the value of R. But now, how do we actually decide what would be the good value of R for our distillation column? So now, just now, one limiting case for R is the total reflux. From total reflux, we get the minimum number of stage. So this is, so for total reflux is the maximum reflux that we can operate with theoretically. So minimum reflux ratio that we can operate with theoretically is called the Rmin, okay, minimum reflux ratio. So Rmin is the reflux ratio that will require an infinite number of trays for the given desired separation of XD and XB. And when you operate a column at minimum reflux ratio, it will correspond to minimum vapor flow in the tower, thus minimum reboiler and minimum condenser sizes or requirement. Okay, so you know the equation here, the ROL, okay? So when R is decreased, so when you, this is your operating R. So when you want to find R mean, you want to find what is the smallest value of R that you can achieve technically. So when R is decreased, the slope here, because this is mx plus c, right? So the slope m, R over R plus 1 will also be decreased. So you want to go, you want to see how far it can be decreased. And if you decrease it further, it will intersect with the Q line. Okay, if you decrease the R further, the slope is decreased, and then initially, let's say this is your R, R over R plus 1. So when you reduce this, you will move towards here. I mean, it will become flatter and flatter. Okay, so it will move further from the 45-degree line and closer to the VLE or equilibrium line. So this will result to an increase in the number of stages, because when you reduce the R, and then your line will become closer to the VLE curve. So when you step off closer to the VLE curve, you will have more triangles. Thus, you will have more number of stages. So this point, P here, when you reduce the R further and further up until you touch the equilibrium line, you will get to this point P here. So this point P is called the pinch point. So what is pinch point? So the pinch point is where the two operating lines of equilibrium line XY curve. So here is the maximum, I mean not the maximum, this is the limit already. You cannot reduce the R any further, because if you reduce the R any further from the feed line, then you will cross the outside the VLE curve, and it will no longer be thermodynamically consistent. Okay, so that's why this is the pinch point. This is the limit to which you can reduce your reflux ratio. Okay, so after you get this point, this will result to an increase in the number of equilibrium stages, and the number of equilibrium stages will become infinite, because you technically you can't really calculate how many number of stages you require in the middle of this point here. Okay, because technically you can't see what happens there. So that's why we say that at R min, the number of stages become infinite. But just now at N min just now, minimum number of stage, the reflux ratio becomes infinite. Okay, so how do we find the minimum reflux ratio? So, okay, first, okay, you have this XD, and this is your XF, your feed composition, and depend, okay, this is your Q line actually. So in this case, your Q is what? Greater than 1 or less than 1? So looking at the shape or the direction of the Q line, it looks like this is Q less than 1. So you draw the Q line. So where the Q line touches the equilibrium line here is where your ROL with the maximum or minimum upper slope just now. Okay, so this is where you can move the ROL, the limit that you can move the ROL. Okay, so that's why from this you can calculate the minimum reflux ratio here. Oops, sorry. Okay, here is your XD, right? So when you, the thing is from XD, you first of all, you draw the Q line. Okay, so where the Q line touches the equilibrium line, you mark that point. So from that point, you draw another line so that it touches the XD line. Okay, this is XD, your ROL line. Okay, so from there, you take note of the Y value of the point P and the X value of the point P as Y prime and the X prime. So the slope of the ROL now becomes R min over R min plus 1 equals to, just the slope is just Y1 minus Y2 over X1 minus X2. Okay, so in this case, the Y1 is the same with XD because we are using XD, so our value of Y is also XD. So XD minus the Y prime. The Y prime is the one that we read from the point P over X1 minus X2. So our X1 is still XD because we are still using XD. And the X prime is the X coordinate of the point P here. So from here, you can get what is the value here, and then you can rearrange to get what is R min, the value of R min. Okay. So limiting cases though. So this is for a highly non-ideal binary system. So, if you compare this VLE curve with the one that we saw here, you can see that from this one is a highly ideal binary system. But if you have something like this is a highly non-ideal binary system. Okay, this is like ethanol water where you have a azeotrope, for example. It's very difficult to. This is the only limit that you can separate the mixture, because beyond that you cannot anymore separate them because they have the same compositions already, like azeotrope lah. Okay, so let's have a look at a highly non-ideal binary system. The pinch point can occur above or below the feed stage. Okay, for example, in this particular example, this is your feed stage. Okay, feed, and this is your Q line. So if you draw the Q line here, touches here, and this is your XD. If you draw a straight line from this point touching this point, you will get the line outside the equilibrium curve. So it cannot happen. It's just not possible. It will violate the second law of thermodynamics. Okay, so how do we calculate the minimum reflux ratio in this case? Is that we need to draw a tangent to from here to close to the equilibrium line. So this one. So find a point close to the equilibrium line to draw a hypothetical pinch point, like a tangent that goes through the curve and also the XD. Then you stretch that point. You stretch that line to get the L over B minimum. So this will give you, the slope will give you R min over R min plus 1. This is for highly non-ideal binary system. Okay. So Actually, a column, it cannot operate at the R min. This is just for us to know what is the minimum reflux ratio, so that at least we know that we cannot designate a reflux ratio value R that is less than R min. It's just not possible. Okay. And then how do we determine the optimum reflux ratio? Okay, now we know that distillation columns can operate between the two limiting cases. Okay, one is for reflux ratio, it can be between R min and infinity, total reflux. And for the number of stages, it can range between the minimum number of stages and infinity. Okay, so the situation here is vice versa actually. It's like, so at total reflux, it's N min. At N min, N equals to infinity. And at N min is R equals to infinity. And at N infinity is R min. So we cannot really operate at this condition, but we want to know what is the number so that when we design the column, we must operate in between these two values. Okay. So as R increases, the number of plates will decrease. And when that happens, the column diameter will increase. The reboiler steam and condenser cooling water requirement will also increase. So the optimum value of R is set between 1.2 to 1.5 times the minimum reflux ratio. So that is the ideal, but this is not a rule. This is just an observation from the practical point of view. Okay, by practice, by experience, people have found out that the optimum reflux ratio is between 1.2 and 1.5 times the R min. But this is not the rule. Later when you do IDP or design project, you can have R as far as 4 times R min. It doesn't really, it's not wrong. As long as you can reach a reasonable number of stage and you can reach reasonable diameter and condenser and reboiler steam heating and cooling requirement, it's okay. This is just generally people put this as a normal value, but it's not wrong to go beyond these values. Okay. So here on the range here, you can see what happens when you operate towards the total reflux. Then you will have a higher operating cost because you will need higher value of steam and cooling water requirement, heating and cooling requirement. But when you decide to go towards the extreme of minimum reflux ratio, and then the N is approaching infinity, I mean the N increases, thus you will have to deal with higher capital costs, although you will reduce your steam or heating and cooling requirement. Okay, so let's have a look at the next table. So this is an effect of reflux ratio on the annualized cost of a distillation column operation. So this is a ratio of R over R min, meaning when R over R min equals to 1, you are actually operating at R equals to R min, and then the actual number of stage become infinite, and you can estimate lah the diameter and then the reboiler duty and so on and so on. So then you can try to calculate the total annualized cost. So as you can see, when the ratio of R over R min increases, meaning R over R min, for example, equals to 1.75, then R equals to 1.75 times R min, right? So as you increase the reflux ratio, you will see that the number of plate decreases from 29 to 13. And then the diameter also initially 6.8, it will increase. And then the reboiler duty will increase, the condenser duty will increase. So this is an estimate of the annualized cost for capital, for equipment, and these are for operational costs. Okay, OPEX and CAPEX. So when you try to calculate the total annualized cost, okay, you have to take into account both CAPEX and OPEX. So you can see that the cost is increasing as you increase the number of the ratio of reflux ratio. Although you manage to decrease the number of plates, but then the total annualized cost looks like it's increasing. So we have to find what is the optimum reflux ratio. So you can plot a graph. Okay, you can plot a graph. So this is the x-axis is the reflux ratio. Okay, from 1 to let's say from here just now until 1.75, and then you can try to extrapolate. And then for this, okay, this is the fixed charge, okay, capital cost, and this is the OPEX. So the total annualized cost is this plus this. So you can see that increases. So that's why people say that you have to operate within an optimal value. So maybe between 1.2 to 1.5 times reflux ratio is where the optimum value is. If you increase further, then you will have to deal with a higher cost. So that's why we come up with the optimum reflux ratio being 1.2 and between 1.2 and 1.5 times the minimum reflux ratio. So let's do an example. So example 1 here. So recall the example 2 from the week 2 lecture. So it's the same liquid mixture here. So you have the liquid mixture of benzene and toluene to be distilled in a fractionating tower at 180 m. Okay. So the feed is 100 kilomole per hour liquid containing 0.45 mole percent benzene and 0.55 mole percent toluene. So XF here is 0.45. Enters at this temperature and blah blah blah. You can read. So here, different from the previous lecture example, in this example, we just want to focus on calculating the minimum reflux ratio R min and the minimum number of theoretical plates at total reflux, and we can do this for part B using graphical and analytical method. Okay, so from last example, you can calculate the Q. Q here, please refer to previous example. Q equals to 1.195, and thus the Q line equation is y equals to 6.13x minus 2.31. Okay, so this is your Q line equation, but the rest are the same, meaning the vapor liquid equilibrium data yx and then the ROL the same. Okay, refer to that example. But then we don't want to calculate the ROL here. It's no point. We just want to know what is the minimum reflux ratio. So what you can do is, okay, you need to do it on your own. This is what the already completed example. So first you plot the VLE curve. VLE. Okay, you plot the VLE curve using the same equilibrium data, benzene and toluene at 180 m. And then you plot the Q line. Okay, so the Q line equation I gave you just now. So you plot the Q line and the VLE curve. And the XD is what? XD is 0.95. Okay, 0.95. So this is your point XD for your ROL, right? But now we don't use the ROL because we want to find out what is the R min. Okay, so just take the point XD, take the point where the Q line intersects with the VLE curve and connect the 2 points, you will get this green line here. Okay, you will get the green line here. So this will give you the X prime. So if you read from the graph, the X prime is about 0.49 and the Y prime is 0.7, about that. Okay, so from the definition, or not definition per se, but this is the slope of your ROL at minimum reflux ratio. Okay, slope of ROL at R min, at minimum reflux ratio. So recall the slope of ROL is R over R plus 1. So at R min, you will have the slope as R min over R min plus 1. So the slope is just the distance between the Y and Y divided by the distance between the X and X. So that's why you just fill in the numbers here. XD is 0.95, Y prime is 0.7, and XD again is 0.95. And then X prime is 0.49. I think you will get R min is 1.19. Please check whether this is correct or not. Please check. Okay, so that is how you get the minimum reflux ratio. Next is to calculate the minimum number of stages. So first you plot the VLE. Okay, VLE. Right. This Q line is not really useful here, but just to indicate to you, this is still the same Q line as before. So simple, using graphical method is not that bad anyway. So from VLE and Y equals to X line, so you just take note of where XD is, 0.95, and where XB is, 0.1. And then you step off the stages from XD to XB when Y equals to X. So this is 1, 2, 3, 4, 5. This is actually 6, but we don't actually go all the way to 6 stages. So yeah, we stop here, maybe around 5.8, including reboiler. Okay, includes reboiler. Okay, so that's how we get the minimum number of stages using graphical method. So next is you can also do part B using Fenske equation. If you don't want to use graph, you use analytical method. So this is the Fenske equation just now. But here you just need to calculate what is alpha 1 and what is alpha b. So you have to have a look again at the graph, the BLE curve just now. Okay. So you have to find out, this is your y1. So you have to read from that, you have to approximate a bit here. Okay, so it's about 0.885, about that. Okay, it's between 0.8 and 0.8. Wait, 0.8, 0.9, right? Okay, all right, tak apa. Let's say 0.88. This is your x1. Okay, xa at plate number 1. Okay, and then you can calculate the alpha 1 as ya at plate number 1 over xa at plate number 1 divided by yb at plate number 1 over xb at plate number 1. So from here, ya at plate number 1 is same with xd is 0.95, xa1 is 0.88, and then for yb is 0.05 over xb is 0.12. So you get alpha 1. This is your number. And then for alpha at bottom of the column is y of a at the bottom divided by x of a at the bottom in equilibrium. Okay, the equilibrium relation. So xb here, you can read what is your yb. Okay, yb. So it's about, say, it's about 0.21. Okay, so b, xb, b, so 0.21 over 0.1 divided by 0.79 over 0.9, then you get your alpha b. So after you get alpha 1 and alpha b, you can calculate the geometric mean of alpha AB, and from this you can put inside the formula, and xd you already know 0.95 and xb is 0.1. Then you just try to solve this and you should get the value of n mean almost similar to what we get up there when using the graphical method, because just now when using graphical method we get about 5.8 including reboiler. Okay, but in this equation, we already minus 1. So whatever value you got here should be almost close to 4.8, around that range. Okay, you should try it out on your own. Okay, so that's how we got R min and N min. So I'm going to stop here before we continue with the next session, the next video.